off on resonance. Resonance here, which carbons of the above, aniline, are most electron rich? It was the ones adjacent to the amine and the one so-called para. So boom, boom, yeah, we did that. Moving on to these two compounds, now we have an extra group added. We have potential for more resonance structures. Potential for more resonance structures. Now you can draw the same resonance structures as we drew up there. And actually you can just do that. Draw the same ones for up there. But then look at your resonance structures and say, okay, which one can I draw one more? Now there's a number of questions here I want you to do on your own, and I will send out an answer key. For example, we take the resonance structures we draw up there. Lone pairs in that carbon, we'll leave a little space. Didn't we have this resonance structure drawn up there? Was it one of them that? With the lone pair here on this pair? Okay. Now we can go, we can keep going, we can draw another one. But let's look down here. What if this group was here? That is, same resonance structures, but what if this group was there and we look at this resonance structure? So look at that right there and draw that. Draw that fresh. Question? Yes, it's going to be able to go both ways because not only can these electrons move here and these move out, but now we can look at the other group that's there now. And we're moving lone pair, and the lone pair is electrons in, electrons out. Now the mechanisms, there were some mechanisms where it's like, unfortunately, some answers are as if you've never seen a mechanism before. Mechanisms are crucial for organic chemistry. Every time you use an arrow, what should you say in your mind? These electrons. Okay? I saw many students having H plus and doing this. H plus has no electrons. So if you said these electrons, I mean, there's no electrons. So this is a no good arrow. So what can we do here? And when we do resonance, we're doing mechanism arrows. Now we're not going between different compounds, but we can use our mechanism arrows, or sometimes called curly arrows. Look it up. Do Wikipedia curly arrows. You'll get a huge old discussion. Y'all use Wikipedia? Okay. I know some professors used to say, "Oh, Wikipedia is bad." No, Wikipedia is great. Okay. Anything you read, you have to have some bit of skepticism, but I rarely see anything wrong. Now, I see things wrong in Wikipedia, but I also see things wrong in the textbook and chemical journals, like typos or just something that's, well, who did this? Wikipedia is great, and any topic we cover, look it up. Full discussion. Okay, these electrons, we can move them in here, electrons in, electrons out. And we get resonance arrow, double-headed. And what does this arrow movement give? We didn't do anything there. But now we have double bond between the carbon. And now these electrons move out, and we start with 2 lone pairs. Now there's 3 on the oxygen, and that's a minus charge. So we can have an additional resonance structure. So with this compound here, you can have an additional resonance structure. This one up here, you cannot. Okay? I'm not going to sit here and draw them all out for you and show you cannot, because all you got to do is draw the same ones, put the group on, and see. You cannot do it. And if you do it and say, well, I don't understand why you can't do it, that should tell you something. That tells you that you don't understand moving the arrows yet. But if you don't get to that point, I don't know. So, what's the question down there? Question is, what amino group that you've come is most electron rich? Well, this one you can do more resonance structures, as shown here, and I just told you this one you cannot. So which one's more electron rich? Which nitrogen, which amino group is more electron rich, top or bottom? The fact that we can do more resonance structures means that these electrons are not only spread out in the ring, but they're also spread over onto this oxygen. Because now the oxygen has an extra lone pair. And it's like these electrons are moved. This oxygen is pulling these electrons all the way over. And the oxygen is becoming minus, leaving, okay? So if this is pulling these electrons way over, is that going to make this nitrogen more electron dense or less? Less. It's got less electrons now. The electrons are more moved over here. But you can't do that here. You can't move these electrons over here by resonance. Thus, these electrons are only delocalized into the ring. They're not delocalized way over here. This guy's more electron rich. This guy, the lone pair, is more delocalized by resonance, not only into the ring, but also into this ketone group. That guy's more electron rich. Which compound would be more basic, top or bottom? Now, means typically basic, but which one's more basic? The one that's more electron rich, right? The electrons are going to react with the H+. If the electrons are really not on the nitrogen, how are they going to react with H+? Another way you could ask is, which nitrogen has more partial positive charge? This one, because you're going to get more resonance structures with positive charge on the nitrogen. This is less delocalized. The more you delocalize this, the more you have partial charge or partial positive on nitrogen. So there are lots of ways to assess your understanding of resonance. Now I'm going to send out a key and it'll have all that drawn there, but you need to do it on your own before you look at the key. Questions about that up there? This type of thing will be very important when we get to the benzene chemistry, because we'll have substituents on the ring, and we'll talk about resonance of one group with another, when it's there, when it's not there. It all comes from just being able to draw resonance structures and then assessing them. Okay, we'll move on to B then. What are we under? B is under something. What A and B fall under what? Again, I beg you to look at the headings, to organize your thoughts. What are we doing here? That's what I want to know. I want to know, what are we doing here? How is it set up? What do we need to be focusing on? We're doing neutral molecules, right? Contain heteroatoms. What's a heteroatom? It's a non-carbon and also non-A. It's like nitrogen or boron. Everybody knows boron, the boron on the periodic table? Neutral. We started out with neutral, okay, on the very first page. But that was just a hydrocarbon, and I talked about how it's hard to show dipole because it's just all just carbon. I actually showed a carbonyl, but we're back to a neutral here. This has a dipole that we could have judged during week 1. Okay, partial minus, partial plus. But 2 days ago, we said that pi bonds are uniquely or very polarizable. And I probably showed it, but I'll show it again from the start. These electrons can actually be moved up to the oxygen. I'm going to go this way. You got room on your paper. There's the resonance arrow. What does that electron movement give? The oxygen now has 3, that's a minus, and that's a plus. Pi bond has been polarized towards the oxygen. Pi bonds are very polarizable. They're not held that tightly compared to sigma bonds, sigma electrons. But see here, because the oxygen, we see that it makes sense it goes that way. Now you would never move it the other way. You would never move them, I'm not going to show the arrow, but you would never move them this way and put minus here and leave that plus. That's theoretically a resonance structure. Because it has the same connectivity, it's just a different positioning of electrons. This is a very bad resonance structure because it doesn't go with the trend of the polarity that's here. Why would you want to show more electron density on the carbon and not the oxygen? Also, does that oxygen have an octet? 2, 4, 6. No. Golden rule. Number 4, with an exclamation point. Electronegative heteroatoms like oxygen should always have an octet. No octet. Very bad. This oxygen will hunt you down and make you regret showing it as a no octet form. Okay? Terrible. Polarization toward the oxygen. Octet, minus charge. This thing is fits the trends of chemistry. Very important resonance structure. Which one's major, right or left? Well, this is major because there's no charge separation. You see, but this contributes a good bit. What does the true structure look like? Somebody describe the bonding between the C and the O. Is it single? Is it double? Now, is it exactly 1.5? Are these exact contributors, and then is it an exact blend of 2 and 1? Or does it look more like which one? It's more like this one. That's why it's major, right? So is it closer to 2 or closer to 1? It's closer to 2, but it's not fully 2. Now, it's hard to show. We usually just show something like this. It's somewhere between 1 and 2. But if we had to say, it's going to be more double bond character than single because this is the major form. The child looks more like mom. Now, what's the charge on the oxygen? Is it really neutral? No, it's partial minus. We see that because, see, it's a composite. The true structure, if we can look at it, that's the true structure up there. Take a picture of the electron density. That's called the resonance hybrid. And the bond order between the C and the O is somewhere between 1 and 2. This is resonance. But this is the trend. You would never do this, okay? Bad. Heteroatom has a pi bond. Yes. The original. Lone pairs. 2 lone pairs, right? What type of orbitals are those lone pairs in? Should have been able to answer this for test 1. What type of orbitals are those lone pairs in? I get a lot of students who say those are p orbitals, and I'm like, no, that's not right. I don't know why you would say that. What type of orbitals are lone pairs in? Anybody? We spent a week on this, and I showed you how to graph it and stuff. How many bonds? What's the hybridization of the oxygen? sp2. Okay? sp2 is this setup, right? What type of bonds do you see the oxygen making? Sigma to carbon and pi bond to carbon. Where are the lone pairs? Here. 2 lone pairs are in hybrids, sp2 hybrids. They're not in p orbitals. The p orbital is being used to make that. But we spent a good week on that topic. Why? So when we move forward, you're able to quickly understand structure. Now, since these are not in p orbitals, are you ever going to do resonance with these lone pairs and do the resonance thing on the board? No, because when you do resonance, you only move pi electrons. Pi electrons are the two between here, and that's the only thing we move. So you got to know where electrons are, what type of orbitals they're in. Go back up top to aniline. Up here we moved that lone pair, right? We did resonance with it on the board. What type of orbital is the lone pair in? The answer better be P, or we should have resonance. But isn't that lone pair up there in the p orbital? Because anytime a lone pair is next to a p orbital, we said it will be in the p orbital? Yeah. So that lone pair is in the p orbital. These down here are not. You got to know where your lone pairs are at. Believe it or not, everything we spent time on test 1 is very important as we move forward if you really want to fully understand what's going on here. Okay, draw all possible resonance structures for this cation. Take time to do that here. There's only one. There's only one good one. I mean, you can theoretically show lots of bad ones, but there's rules, and those rules help you to tell you basically don't draw the bad ones, don't show the bad ones. Lone pairs here. These electrons move here. So that is going to give the bond F there, positive charge on the fluorine. That's it. Any questions? What are you thinking about that? Was there another one you wanted to draw? That's A. You want to move these down here? And get this. Talk about this here. Well, what did we just say about oxygen and no octets? That oxygen does not have an octet. Let's go to rule number 4. Never do that. Terrible resonance structure. Now, if this was carbon, that'd be okay, because carbocations are okay. Form carbocations all the time. Not an electronegative heteroatom. Any questions about this here? Positive charge on F. Is that bad? It's okay as long as the F has an octet. 2, 4, 6, 8. The F has an octet. It's okay. Charge is delocalized. Is the charge just on that carbon, or is some of the charge also on the fluorine? If you drew the hybrid, you would have some of the charge is on the fluorine. The charge has been delocalized. If we can delocalize the charge, that's a stabilizing effect. That's it. Which one's major, left or right? This one, what? More bonds, even though that fluorine has a positive. Okay, effect on acidity. Well, we covered this back in the acid-base handout during test 1. You should pull out your acid-base handout. There's a section. There's 4 things that affect acidity. One of them was resonance. Talked about it. We didn't fully introduce it, obviously, but we sort of gave some take-homes, set the stage. Here's the trend. Alcohols, standard alcohol, ppm about 16. A phenol, more acidic, ppm 10. Carboxylic acid, even more acidic, ppm 4. Why? It's resonance. Okay? You need to look at this on your own. You need to look back at the acid-base handout. You need to see what type of questions you might have about it. All right? You don't want me to stand up here and be the evil genius. You know what an evil genius is? Someone who just tells you everything and then, okay, let's move to the next topic. No, you want to be, hey, can I do the problem? Let me do the problem. Because if I do the problem, then I'll learn. If you just tell me, then, well, okay, so look at that. That's actually going to be on the key, answer key that I send out. Acid-base handout. General trends of how do you predict stability. What do you really want to look at here? The stability of what? What? When we were doing assessing acidity, what did we really look at? The stability of the conjugate base, right? We didn't just do that back then and never do it again. That's how you do it. You want to assess the stability of the conjugate base. Resonance is a great stabilizing effect. How do you stabilize a minus charge? Move electrons towards it or away? Away. Okay. There you go. You'd be able to explain that trend there. There's actually a very good question that should hopefully be asked there that I'm hoping to hear. It's a little bit counterintuitive. I'm comparing two. Then we come down here, which is more acidic. Okay? That's phenol, but what if we put a nitro group here versus here? This is called a nitro group. It wasn't on our functional group list. We'll see it in organic too. If you have me, you'll actually make a nitro compound. You'll nitrate something. The Lewis structure for the nitro, we'll draw it out. Double bond to oxygen, single bond to oxygen. And this is coming off the ring. Now you could hopefully do this yourself. This is the structure of the nitro. It's going to always have two charges. You can't draw it without any charge. It's net neutral though. Net neutral group called a nitro group. Nitroglycerin has nitro groups. Trinitrotoluene has 3 nitro groups. What's trinitrotoluene? TNT, trinitrotoluene. Need to be able to draw resonance structures. Okay? We've already drawn resonance structures of phenol. Well, actually, we did the anion. So you can make it neutral, and when it's neutral, it's just like if it was NH2. Then you put this group out here, and it's just like the question with the aniline. Can we draw additional resonance structures into the group? Well, for one of them you can, for the other you cannot. Then you say, okay, well, how is that going to affect the acidity? Then you're able to answer. Effect on basicity. Same trends we could have had on test 1. This is a standard amine, sp3 nitrogen. This lone pair is an sp3. Standard saturated amine, ppm about 10. Of course, this refers to the conjugate acid, right? Aniline. Is it more basic or less basic? You should be able to tell that 2 ways. From the number, less basic. From the structure, less basic. Why is it less basic? Because the lone pair is delocalized by resonance. If the lone pair is delocalized by resonance, it's not sitting there on that nitrogen acting as a base, or can act as a base. Aniline has some basicity. Yeah, okay. What functional group is that on the right? or amide, however you want to say it, right? Amide. Amides are considered non-basic. Okay? But you need to be able to explain that trend. Now, we probably said something earlier about basicity of nitrogens. Didn't we say that anytime a lone pair is in a p orbital, it's not going to be basic? Pretty sure we did. Well, this lone pair is in a p orbital. It has slight basicity. Very slight. Okay? But if you go by what I say, then you should say, hey, why is that saying non-basic? Well, it's because it's sort of an exception. Then we can ask questions again. Well, which nitrogen is most basic? Draw resonance structures. And again, in one of these, you can draw resonance structures from the lone pair into the group. The other, you can't. You are going to start with the lone pair here, right? Resonance of radicals. You can do resonance of radicals. I think I'm going to delay that. I think we'll talk about radicals near the very end of the course. But radicals can also be resonance stabilized. Okay? Any questions about the golden rules of resonance? Okay, so that's resonance. Again, I'll send out an answer key to some of those problems on that handout. The next topic is chemistry of dienes. This would be a diene, of course, diene, two enes, a compound that contains two alkenes. Okay, dienes. Dienes can react with reagents just like we saw that monoalkenes can. Okay, for example, we can react with HBr. But what we're going to see is there's kind of a little twist. You can actually get different outcomes depending on temperature, cold versus hot. Okay? We'll be looking at a specialized reaction called a Diels-Alder reaction. This is a reaction of a diene reacting with a monoene. Type of product does a Diels-Alder give? Once you know, you can easily answer which compound can be made from a Diels-Alder reaction. Diels-Alder, very important reaction from the mid-20th century. You can also have more than diene. You can have trienes, tetraenes. Maybe you have 11 alkenes. At that point, you start calling it a polyene. You just have many alkenes, polyenes. I mean, these are examples of polyenes. You ever heard of amphotericin? It's an antifungal drug. It's a polyene, all these alkenes. Okay? Well, let's wait till we get into what temperature does first. But it can be even more possibilities. Accutane used to treat acne, you know. So those are just examples of polyenes with multiple alkenes. Of course, Accutane also has the carboxylic acid, etc. Okay, so a little warm up there. First thing we'll look at is nomenclature. We'll do that here. We've already looked at conjugated versus non-conjugated versus cumulated. That was in the other handout. Let's look at nomenclature. Just like alkenes, except we're going to have a little bit of variation. Longest continuous chain, 1, 2, 3, 4, 5, 6, 7. That would be what? Heptane. If it was just one alkene, it would be heptene. And then you would denote where the alkene is. What about when there's two? You put diene on the end. This becomes heptadiene. Okay, this is how you do it. What if there were 3 triple bonds? Heptatriene, etc. We're only going to do dienes too. So this is how you would do it. Longest continuous chain. The 2 alkenes need to be in the longest continuous chain. But then you denote where the alkenes are at. First off, which is the one end, left or right?
Right.
That's 1. So this alkene is at the 2 position, and this one is at the what? 4. So this is a 2,4 heptadiene, with this indicating where the alkenes are located. So what is that over there? It's also a heptadiene. It's also a 2,4 heptadiene. It's the same exact name, right? Those are stereoisomers. They only differ in... You also have to denote E or Z. Is the alkene in the 2 position E or Z? E. How about that one? They're both E. Put E, comma, E at the beginning. That's that. What do you want to put in front of this one? What is this alkene? That's Z, and this is E. We would say Z, comma, E. Z, comma, E, 2,4 heptadiene. When you do this, the first letter goes with the first number. This letter goes with the next number. That's the EE isomer, and that's the ZE isomer. You could also have the ZZ isomer. What's the relationship between those 3? What do we call them? Are they cousins? Best friends?
Stereo.
What type of stereoisomer? Diastereomers. Yeah, they're diastereomers. Right? Well, not mirror image. The mirror image of ZE is ZE. Stereoisomers are not mirror images, diastereomers. Okay, name this guy over here. What's the longest continuous chain? Six. Hexadiene. Why is it not 8? The longest continuous chain have to contain the alkenes. Just like if it was one alkene. The diene, they both need to be in the longest continuous chain. Okay? What's on the hexadiene? Which is the one, left or right? Here you have a 1 alkene, here you have a 1 alkene. how are you going to break the tie? Well, here you would also have a 1-chloro, where here the first substituent would not be until over here. This is a 1. So one alkene's at the 1, the other one's where? 5. So 1,5-hexadiene. What's on the 1,5-hexadiene? A chlorine and a propyl. We put these in alphabetical order. Chloro is 1. Propyl's at what position? 2 propyl. 1,5-hexadiene. Is there any stereochemistry possibilities that we need to differentiate? Yes. What do you want to put in front of this? E. Why would you what? What other alkene is E?
Oh,
this alkene is not stereogenic. It's not E or Z, it's neither. Not alkyl. That one's E, right? Because here we have chlorine, and here it's the same, but this carbon has another carbon. So high priority groups are opposite. E. The E refers to the stereogenic alkene, not to the other one. It's not stereogenic. How's that name look? How many stereoisomers are possible for that compound? Total. 2 total. This one or Z. This could also be Z. 2 total. Okay, that's nomenclature. Should be pretty consistent with other nomenclature, yeah? Another sort of application here. Dienes or polyenes, you see a lot of them in nature, natural products. For example, retinol, polyene, okay, synthesized in the body from beta-carotene. Squalene, I know it's very prominent in fungal organisms. Antifungal medications and creams, they often inhibit the enzyme that works on squalene in the fungal organism. All these types of compounds here are called terpenes or terpenoids. Terpenes are essentially dimers and trimers and tetramers of the building block here, which is actually a very simple diene. You could name it. What's the name of that? It looks like it's 1,3-butadiene with a methyl at the 2 position. 2-methyl-1,3-butadiene. Yeah. Better known as isoprene. Isoprene is the building block for making all of these. It has 5 carbons. Well, this has 10 carbons. That's 2 of these reacted to make that. What type of mechanism? Magic? Or can we show a reasonable mechanism supported by theory? You react this with a little H plus catalyst, and you could get there by a mechanism. Now, the little difference between mechanisms that we were doing is we were doing addition reactions. You know, there's really no addition here. There's no like OH or halogen because it ends with an elimination. And we'll be covering eliminations in the next couple of weeks. It's very standard chemistry. But these plants and fungal organisms can make very complicated, structures. But these structures that come from isoprene are known as terpenoid or terpenes. Terpenoids. What's another class of natural products? What was the other class we looked at? Alkaloids. What's an alkaloid? Those are natural products that contain a basic nitrogen. Yeah. Well, these are not alkaloids. There's no basic nitrogen. All these are examples of terpenes. Okay? You can recognize these because they typically have multiples of 5. See 5? 10, 20, okay, 30, 40. They all, it's a quick way to recognize that it comes from that. Beta-carotene. Taxol. How does the U tree make that sophisticated molecule Taxol that we use for breast cancer? Isn't that amazing? Okay, reactions of dienes. Let's introduce this real quick. Largely two types of reactions. One is called 1,2 addition. The other is called 1,4 addition. Here's where we got the temperature. You take this diene reacted with HBr under cold temperature, you get this product. This is a standard mechanism we could have did 3 weeks ago. Please do this on your own. Have it here for next time on Monday. Okay. We'll look at it. We'll give it some terminology. We're going to call it 1,2 addition. It's going to be nothing new. Then we can come down here and do what's a little bit new is going to be called 1,4 addition. How do we get this product? Well, it starts the same way up there, except our intermediate cation, guess what we're going to show on the board for it? Starts with an R and a res. We're going to show resonance. And if you show resonance and then continue, you'll be able to get the other product. It just comes from invoking a resonance structure, which is there anyway. Because the resonance gives you two forms to consider, or maybe more. One product comes from one resonance structure, the other product comes from the other. That's all that's going on here. But there's some details, why the temperature difference, etc. Okay, reaction coordinate diagrams, etc. Guys, have a safe weekend. If you're out on the road trick-or-treating, okay, make sure you have an adult with you. Flashlight, okay. Be safe, okay. Lab this afternoon. We'll meet downstairs. Have a good weekend.